All right, you guys. So for number 7, we are now starting section B. And so we need to go over some problems that are a little bit longer. So for number 7, we have the temperature of a cup of tea, T minutes after it is poured. So T is minutes after it is poured, can be modeled by that function right there. And they also tell us that T has to be greater than or equal to 0. And so on the one hand, this is what we call the domain, okay, because it's defining my values of x. X in this case is going to be T. And so this is your domain, which is basically possible values. Okay, possible values for x. And I'm going to put x in apostrophes because in this case, x is really like your T, right? Like literally your T minutes, not cup of tea. T minutes. And so here it says basically that minutes has to be greater than or equal to 0, which is, in other words, that time has to be positive or equal to 0, which, makes sense, okay? So I'm just pointing out a little bit of the context of the problem and that the temperature is measured in degrees Celsius. And so if you, for example, plug in a T equals 2, you're going to end up with some temperature, which will mean that after 2 minutes, the T has that temperature, okay? And so that is the main idea. You plug in time, you get a temperature, okay? So at T equals 2, what is the temperature? That is what would happen if you plug in T equals 2. That is the context of the problem. So enough blah blah, let's jump into it. For part AI, we need to find the initial temperature of the T. Now, this is a classic question that shows up all the time. What's the initial temperature? What's the initial height? What's the initial whatever, right? Who knows? See? And so the moment you're reading the word initial, you need to be considering that initial is like it's the start of it, right? It's the beginning, all right? It's the first thing that happens. And so the initial temperature of the T has to be, think about it this way, as early as possible. And how early can you go? Well, how low can you go with your domain? T has to be greater than or equal to 0, and so the initial temperature of the T is going to be at T equals 0. And so actually for part AI, what you're going to be doing is plugging in 0 for T, which means that you end up with 21 plus 75 times e to the power of negative 0.08 times 0, which means that you end up with 21 plus 75 times e to the power of 0, and anything to the power of 0 is equal to 1. So this is the same as 21 plus 75 times 1, which is just 21 plus 75. All right, so anything to the power of 0 is equal to 1. You can remember that as a rule of thumb. Um, and just a very quick explanation of why something to the power of 0 is equal to 1. My favorite explanation is the following. So if you have 2 to the power of 3, it's the same as 2 times 2 times 2 equaling 8. Now technically this 2 times 2 times 2 also has at the very end, and this is key, it also has at the very end a times 1. Alright, technically all numbers are always multiplied by 1, and that's going to help for my explanation in a second. So 2 squared is going to be 2 times 2, and also times a 1, right, equaling 4. 2 to the power of 1 is going to be 2 just once, because it's 2 to the power of 1, times 1 is going to equal 2. And so technically, as you can see, this 3, right, makes you have 3 2's being multiplied there. This 2 makes you have 2 multiplies, 2 2's, sorry, being multiplied there. And this 1 makes you have only 1 2 being multiplied. And so the moment you have 2 to the power of 0, well, when you look at that, you end up with only the green number, only the 1, so it has to equal to 1. See? So that is one explanation that you can sort of like dig into. The other one that I like a lot is that technically, if you want to go from, for example, from 2 to the power of 1 to 2 squared, well, what do? You multiply by 2. If you want to go from 4 to 8, what do? You multiply by 2. And again, if you want to, multiply again by 2, right? You would end up with 16. So 2 to the power of 4 is 2 times 2 times 2 times 2 times 1. Now, what if you want to go backwards? So if you want to go from 16 to 8, you have to divide by 2. from 8 to 4, you have to divide by 2. You have to divide by 2. And eventually you do 2 divided by 2 gives you the 1. Okay? And so basically, with any number and any exponent, once once you reach that number to the power of 0, you're going to be doing itself divided by 2, giving you 1. Always. For example, 3 squared is 9, 3 to the power of 1 is 3, and eventually on this step here, you do 3 divided by 3 gives you 1. And so anything eventually being to the power of 0 is going to be itself divided by 3. That's why anything to the power of 0 equals 1. See? So hopefully we learned something new today. But more than anything, you need to have the rule of thumb that anything to the power of 0 equals 1. And E is just a value on your calculator, literally. E is like 2.7 blah, blah, blah. All right, it's an actual number. See? If you actually put in your calculator, it is just above your division symbol. Look at that, 2.718. And so E is an actual number, and anything to the power of 0 equals 1. So yeah, that is why this turns into 1. Okay? Anyways, a little bit of a longer introduction only because I explained some additional concepts. And so for part AI, you end up with 21 plus 75. That should give you 96. Now let me double check, but it does sound good. Look at that, 96 exact. Make sure you put the units in degrees Celsius. See, so this is for part AI. I put it in blue to show my answer just in case. So AI is going to be 96. Then for part for part A double I, we need to find the temperature of the tea 3 minutes after it is poured. And so this is also very straightforward sort of procedure. It tells you 3 minutes after it is poured. And you know that T, as we highlighted earlier, is minutes after it is poured. And so in this case, for part A double I, T equals 3. And so, okay, let's go ahead and find out what T equals 3 is in my function. So if you plug in 3 for T, you end up with 21 plus 75 times E to the power of negative 0.08 times 3. All right. And here, no one's going to do quick maths and figure that number out right away because that is insane. It is crazy. And so thankfully for paper 2, you have your trusty rusty calculator. And so from here, you can plug in 21 plus 75 times E to the power of negative 0.08 times 3. All right, so we double check that everything looks nice and dandy. I would say that it does. You plug in and there it is, right? And so H parentheses 3 gives you 79.99 blah 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 70. See? If you want to do significant figures, you would count 1, 2, 3. See if you round it up or keep it the same. You round it up, so H3 can actually end up being 80. All right, so 80 Celsius. And as you can see in the mark scheme, you can put either of those. You either put the whole number or you put the 3 significant figures. See? Either of them works. Do as you wish. I'm going to put this answer in blue because I want to get into the habit of doing that. I think it's more organized. Anyways, that is the answer for part A double I. Awesome. And now for part B is where this exercise starts getting a little bit crazy. And so you need to write down the value of H, like small apostrophe 3. And so H small apostrophe, let's just go over a little bit of context. See? So there's some weird stuff that they can ask for. Okay, so on the one hand, f of x, you need to think about it as like the original function. Okay? Then you have the derivative. Okay? And last but not least, you also have like the inverse. Okay? And so all these different symbols you have to get familiar with. The inverse is literally like to the power of negative 1. The derivative has that little apostrophe symbol, and the original one is just the original one. Nothing's changed, okay? The other context that we need to establish, because it does show up later for interpret the meaning, blah, 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 okay, is what the derivative actually does, okay? Because we talk a lot about how to get the derivative, how to work with the derivative, but what does the derivative actually do? So Here's gonna go a quick monologue or blah 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 explaining that. If you already know, you can probably just skip ahead. See? The point is, in the original sort of version of your function, if you plug in an x, you're gonna get a y. Okay? And so if you plug in x's and y's into your original function, all you're really getting are x, y coordinates. And when I say x, y coordinates, okay, if I say x and y coordinates, it's a bunch of different points, okay? So in the original one, you plug in x and y, you get a bunch of x and y coordinates, all right? In the derivative version of it, yes, you plug in an x, and technically, yes, you get a y, but the y is now not a coordinate. The y is actually now the slope, which is very interesting. Because for part B, they say write down the value of the derivative when t is 3. And so basically, if you plug in an x of 3 here, it's the slope at x equals 3. All right? And so now suddenly say that your function looks, I'm going to make it up, see? But let's say that your function looks like this. And so at x equals 3, it would give you the slope that is right there. See? And so the slope right here would be, I don't know, it looks positive. It looks like it's increasing. Let's just make up it's a slope of 5. Okay, so this is just a visual example. It has nothing to do with this exercise. All right, this is just a visual example. But my point is, when you get the derivative, suddenly plugging in x, you are now asking your function, what is the slope? See, in the original one, you plug in x and you get a y coordinate. Right, it's very different. In the original, you plug in an x, you get a y coordinate. In the derivative version, you plug in an x and you get the slope at that point. Okay, so that is very important to keep in mind, to understand, so that we can work with it more, fluently. See? And now, the last but not least, the inverse is just kind of whack, but technically, here, you plug in an x, you also get a y. It's also going to be x, y coordinates. There's nothing too crazy here, just for the fact that, well, you're dealing with the inverse, so it's like the mirrored version of your original, stuff like that. See? So I'm not going to get into it. I'm not going to try to graph it either because it depends on every case. But point is, the main thing I wanted to show you or explain is that for the derivative, now when you plug in an x, you're really getting a slope, okay? And yes, it comes in the form of a quote-unquote y value, okay? But now your y gives you the slope, okay? So that's the main idea I'm trying to portray here, and it's going to be relevant down the line. So for part B, you need to write down the value of the derivative of 3, see? So clearly we need to start off by finding the derivative, right? And so let's take a moment and write down h of t. And so h of t equals 21 plus 75e to the power of negative 0.08t. Now, the derivative of this is a little bit hard. See? It's a little bit hard because you have an e going around. Now, thankfully, the derivative of e is very specific. All right, so if you go ahead and go to your formula booklet, it's very useful to get familiar with the formula booklet because the day of the test, it is an additional tool that you can use. All right, so get familiar with it. There is no reason not to. So anyways, eventually you can go to the part of let's go to calculus because we're big boys now, right? And so with calculus, you have a bunch of different derivatives. You have derivative of the exponent, of sine, of cosine, and boom, look at that. I'm putting it in red, the one we have at hand, right? And you have a bunch of other different ones. You have the chain rule, the product rule, the quotient rule, a lot of different stuff. See? And if you're HL, you have a lot of different stuff, okay? But for now, we can just laugh at them because we're SL, not HL, so ha ha ha. We don't have to know so many derivatives. And I can't believe they call them standard because, damn, some of these are wild. See? Anyways, back to over here, the derivative of e to the power of x ends up being quite simply e to the power of x, right? And so the only sort of like detail that I do have to point out here is that you do have a negative 0.08 up top, right? So right now we have 75 e to the power of negative 0.08 times t. And so the negative 0.08 does do something and the 75 does stay. All right. And so you got to keep that in mind. Basically, what's going to happen is that you're going to end up with the derivative version, right? It's going to be 75 times negative 0.08 times e to the power of negative 0.08 t. All right. So what is that? It's going to give you 75 times negative 0.08. So that means up front, you end up with negative 6 times e to the power of negative 0.08 t. And so this is the derivative version of just the e to the power of x, right? So if I go back over here and I find the derivative of this, okay, and I find the derivative of this, on the one hand, that 21 is going to disappear because if it doesn't have a variable next to it, it's just going to disappear, see? So technically this first term is just kind of gone, and the second term, we end up with what I wrote over here, right? So it's just going to be negative 6 times e to the power of negative 0.08 t. And so writing down the value of h, of the derivative, sorry, when t is 3, is just going to be plugging in 3 over here, right? So plugging in 3 over here, you end up with negative 6 times e to the power of negative 0.08 times 3. So let's go ahead and find out what that is. Negative 6 times e to the power of negative 0.08 times 3. Negative 4.719. 4.719 looks good to me. So the final answer basically is, what's the negative 4.7? If you want to think in significant figures, following the mark scheme a little bit, right? You would count 1, 2, 3. Do you round it up or keep it the same? You round it up, so it's negative 4.72. Don't forget your units. Actually, no. We're talking about slope, so you can just leave it like that. See? Now, technically, if you want to put the units, it would be in a kind of wild manner, but this is good enough. See? So the slope is negative 4.72 when t equals 3. All right, so that is for part B. You just got to be really wise on how the derivative works. And so, yes, on the one hand, like the e to the power of x doesn't change, which is why the exponent, as you can see, remained the same all along. But what will happen, which is a little bit whack, is that the negative 0.08 will go down below in front. See? And so be careful with that. That is the only sort of like watch out that I have to point out. See? But once we understand that, the derivative is fairly easy. And there it is. Okay, so that is for part B. For part C, we need to interpret the meaning of your answer to part B in the given context. And so here is actually something fairly interesting that I'm going to point out. This is a context question, all right? And so usually for a context question, you can see that you can answer without having to do like any other part, see? And so yes, it says to interpret the meaning of your answer to part B in the given context, but even without having the answer to part B, you can still interpret it. See? If you look at the mark scheme, I mean, look at this. Here it says you can talk about it cooling or decreasing. You can talk about it at 3 minutes. It means something, right? And only here do you actually put the answer for part B. All right. And so there's a lot of different ways to answer part C. And my point is that because it's a context question, you actually don't need the answer from part B. Now, why would I actually tell you this? Why is this useful in the first place? Because if it's the day of the test, see, and you're running low on time, and whatever, like there was a really hard problem at the beginning, you got stuck on it, and this or that, and blah blah blah. Keep an eye out for context questions, okay? Because maybe you did nothing of number 7, but you have 3 minutes left, and you look at it, and you identify, dude, look at that. Part C is a context question. So you can answer just part C, forget about part A, forget about part B, and probably nail like 1 or 2 free points. Okay? So 1 or 2 free points is always going to be useful for your math grade. Why not? See, so I'm just saying, guys, always be on the lookout for context questions or any sort of part of your question which does not require anything from before. See, for example, just looking at it right now, I can sort of tell you that part E and F, like Well, I guess f you do need the derivative, but technically part e, you can do it by its own. You don't need parts A, B, C, and D for part E. You literally don't. Like, not even kidding, you don't, right? And so you can skip to part E if you recognize that you can do it. If you're low on time, might as well nail a couple points where you can. See, so be on the lookout for questions that don't require what needs everything from before it. Be on the lookout for context questions as well. This is particularly useful if you're running low on time and you need to get some extra points on the way. See? So that is more of a like test taking tip that I'm trying to give you. All right. But anyways, blah blah blah. Back to reality. For part C, it's a context question. We need to interpret the meaning of your answer to part B in the given context. And so here, there's a lot of different ways that you can sort of interpret this, etc. Right? But the main thing that I told you earlier is they want you to know that when you plug in 3, you're getting the slope at x equals 3. See? And so the slope, you guys, easy question, is it positive or negative? Clearly the slope is negative. And so what you can say is that at 3 minutes, so here you already identify that t equals 3, right? Which is the first point that they give you there, right? So at 3 minutes, you can understand that it's 3 minutes. The slope is decreasing, right? And so that is the second point you can get. See, they don't want you to say changing because you have to like let the evaluator know, like, is it growing or decreasing, right? If you say changing, they know you're not being specific. So the moment you say decreasing, you're understanding that this negative 4.72 means that the temperature is lowering because it's negative. See, that's why they don't want you to say changing. They want you to understand that the slope is decreasing. See, so at 3 minutes, t equals 3, the slope is decreasing. And here you can just get like awfully specific and say like at a rate of negative 4.72 Celsius, right? And what are my units? Well, it's units. And so you can say Celsius per minute, right? And so this is a fairly straightforward, it's just a context question. We're just interpreting our answer, right? And you might be thinking, okay, but didn't you need the answer from part B? Well, you technically didn't for this and for this, right? Yes, you needed to mention the rate at which it's at, but you can mention that it's decreasing because, dude, by context, it's a cup of tea. It's going to decrease in temperature. And also that you can understand that this 3 here means that we're talking about 3 minutes. See? And so, yes, it's a context question that you could have gotten both points of quite easily. See, I'm just saying, right? But anyways, that is the answer for part C. And again, I insist, get points where you can. See? I'm just saying, why not, right? Why not give your best? Enough blah blah. Now we go to part D. So for part D, we have that after k minutes, so after some amount of minutes is what they're trying to tell us. So after some amount of minutes, the T will be below 67 degrees, will be below 67 Celsius, and cool enough to drink. The coolest tea in the whole school, cool enough to drink. All right, sure. And so after some amount of minutes, the T will be below 67. And through this, we need to find the least possible value of K, where K is what? K is this. All right. Unfortunately, you are in a math class, and you do have to learn some math terms, okay? So I can teach a lot of this intuitively, but there are a couple things that you just sort of have to know. I'm sorry, this is one of them. See? So I'd rather just be honest with you. This is the kind of thing you just have to know. See? In the math world, when they express something like this, okay, all this is really saying is that K like pertains or belongs to the group of the integers which are positive. Right? So this is a big hint that, dude, all your K values pertain to the integers that are positive. See? This is no different than if someone tells you, dude, all your X values are like even. See? And so, now you know that all your X values are 2, 4, 6, 8, 10, etc. See? Or if someone tells you, dude, all your X values are whatever, like odd. See? So it's going to be 1, 3, 5, 7. It's like that kind of thing. See? Just that we get very, very fancy, and suddenly we're talking about, integers. Fancy. See? And so integers that are also positive. See? So let's first talk about just integers. Just integers are going to be, and actually, let me write this down. So integers, which is the big Z value, right? I mean, the Z um, symbol or whatever. See? So integers, your Z, are just going to be whole numbers. Okay? And so simply whole numbers can be -3, -2, -1. I'm pretty sure 0 is included, right? Then 1, then 2, then 3. See? But the moment that they say integers which are positive, that means boom, boom, boom. You only end up with the ones that are positive. See? And so if it's telling you that k pertains to all integers which are positive, then you know you're dealing with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. See? And so your k values are whole numbers which are positive. That is what it's telling you. See? And it's important to know that in order to answer correctly. Okay? But regardless, the procedure is pretty much going to be the same. So let me make a little bit of space because it will get juicy in here, so be careful, right? So let me make a little bit of space for part D. It says that after k minutes, the t will be below 67. And so let's first write down our original function. See? So our original function is 21 plus 75 times e to the power of negative 0.08 times t. And so technically in this context, t, right, equals time, and h of t, which is like your entire y, ¿cierto? So your entire y is going to be temperature, right? And so if here they're saying that after k minutes, so it's going to be some t, right? So k is like some t. So after k minutes, the t will be below 67 degrees, so that means that your temperature, right, is 67 or below, right? Or actually, it's not 67 or below, it's below 67. Small difference there, see? So that means that if you express that into your original function, what you end up with, okay, is technically that this is temperature, see? And so you're going to have a temperature of 67, but your temperature is going to be below this, right? And so, kapow, right, below 67, 21 plus 75e to the power of negative 0.08 k, all right? And so at some value of k, this is gonna start going like below that. See? Now, this is the initial sort of approach that you have to establish. You put the inequality because we are talking about something that is below 67, so you gotta find all values that give you below 67, right? Now from here, there's a lot of different approaches. I think the friendliest is graphing, but for now, I'm gonna show you the hardcore mathy way. See? And so the hardcore mathy way is like just get your variable alone. Do everything you need to do in order to get your variable alone, which, yes, is in an exponent. But, spoilers, if you have, and I'm going to write this down here, see, if you have variables on an exponent, consider logarithms. Because logarithms have an incredibly useful property, and it's the main reason why you use them in the wild. See, the main reason you use logarithms in the wild is because it lets you get rid of exponents. I mean, it lets you get rid of variables on an exponent. See, if you look at the formula booklet and you go to logarithms, right? So logarithms. You have a bunch of different properties, but there's one that is very interesting, which is this one right here. And so this one right here, notice what happens to m. So m is on an exponent, and then m is in front. So all you're really doing, for example, say you have log of x squared, this ends up being 2 log x. And so it's very useful to get like rid of exponents, see? But even if you had something crazy like log 2 to the power of x, then this ends up being x times log 2, which is a lot more friendly on the one hand, because you don't have a variable in the exponent anymore, and also it might look a little bit nasty because you do have a log. See? So I'll establish how to deal with that down the line, but for now, I need you to have the mental approach, or like the sort of protocol, or the procedure that, dude, if you have variables on an exponent, you can consider logarithms. See? And so from here, just seek to get k alone. And so on the one hand, you can do minus 21, which means you end up with, quick math, 46 is less than 75 e to the power of negative 0.08 k. From here, you can divide by 75. Why not? We can do that. So this goes away with this. 46 divided by 75. I never learned that in school, so let's check it now. 0.613333. 0.613333 is less than e to the power of negative 0.08 times k. And so from here, you can consider using the logarithms to solve this properly, right? And so something that I didn't mention earlier is that you have two types of logarithms, right? So you have like the original logarithm, and you have natural log. See, so this is natural. Okay, so this is natural log. And this other one, I don't think it has like an actual name, but it's, think of like original log. Okay, whatever, original log. Yeah. And so both of these have different bases, right? Technically, you can sort of pick your base in each, but the base, the default, okay, what comes from its factory, right, is that original log has a base of 10. All right, it's like a hidden 10 that is written here. See? And when I talk about base of 10, well, there's a lot of context I need to go over, but basically, so notice here in the definition of log, this small a there, it's the base you use for the exponent later. See? And so that small a for logs is going to be 10, like on its default, unless you change it. And for the natural, it's going to be e. And so this is very useful because, you have an e going around. So that means that on this step here, you can apply natural log to both. So you end up with base e, right, I should say. So, natural log has base e, but just to be very clear, technically you end up with log natural base e, parentheses 0.61333, is less than log base e, parentheses e, and this to the power negative 0.08k, right? And so the first step that we're going to go ahead and do is that technically from here, right, we can do log natural of 0.613333, right? Now, you might be thinking, dude, in your calculator it says log natural 0.61333, but here on the board you're putting log natural base e and then the 0.613333, right? Now, I put the base e just so that we're on the same page that log natural has a base of e, but because it's the default, technically you don't have to write it. So if I rewrite this line down here, really you can just leave it like that, okay? So I was just doing the base e just so that we're all on the same page, but technically it's the same thing, see? Whether you put it or not, it's like redundant. See, it's like, it's the default, it's what's expected. Anyways, so if you plug in that thing on the left, you end up with that number, which yes looks nasty, but let's trust the process. So you end up with negative 0.48, basically just 888, see? Is less than, and here we can apply the famous log property of getting rid of the exponent, which is why we were doing this in the first place, see? And so we're applying this property here, which means that the exponent is going to go down in front, right? And so the exponent goes down in front, you end up with negative 0.08 times k, right? Times log natural of e. Well, log natural of e, if you put it into your calculator, so log natural of e, well, you look at that, it's just 1. And so this is going to be times 1, basically. So it's just going to disappear. How friendly. And from here, you can actually get the value of k. So you can divide both sides by negative 0.08, divide both sides by negative 0.08. And here, it's a quick rule of thumb, but the inequality symbol, this is the thing. If you divide or multiply by a negative, by a negative with an inequality, you must flip the symbol. Okay, and this is just to be consistent with your math. It's just a rule of thumb that I learned early on. Basically, negative 0. Whatever, like this number, see? Divided by negative 0.08 gives us that. It gives you 6.11, right? But you're going to flip the symbol. So instead of being like this, it now ends up being like this. And now you have k alone, see? So that was quite a sort of like long series of math in order to find my answer. So let's really try to interpret this properly. So you just found for part D, you found 6.11 is greater than k. So after how many minutes will the T be below 67 degrees? Well, here it's saying that after 6.11 minutes, it will be below 67 degrees. Now, this is not saying 6 minutes and 11 seconds. It's saying like 6 minutes and 0.11 minutes. Okay? So, important distinction to do there. Think about it this way, it's like a little more than 6 minutes. See? Now, because they're asking for an answer where k is part of positive integers, you need to consider the closest possible integer that makes this answer make sense. So, for example, if you go ahead and say, okay, so k equals 6, this is a small mistake, but we really need to understand why. This is a small mistake because technically at k equals 6, you are not yet below 67. You are almost below 67, but not quite. And so technically, in order to make sure that you're below 67, it has to be something greater than 6 minutes, given what we found, right? And so your answer for part D is going to be that k equals 7. So yeah, just to go over that one more time, because I know it's kind of whack, I know it's kind of weird. Point is, think about it this way. At 6 minutes and a little bit more, the T reaches a temperature that is below 67 degrees. But they're forcing you to answer in terms of minutes. And so if you say 6 minutes, it's not truthful because at 6 minutes, are you below 67 degrees? Not yet. You're almost below 67 degrees, but not yet. And so technically the proper answer is saying 7 minutes. See? So at k equals 7 is the least possible value of k, where k is part of like integers that are positive, where the t will be below 67 degrees. See? And if you look at the mark scheme, well, you look at that. Here's the 6.11 and here's the 7 minutes. See? Here is the inequality, and here's the use of logarithms that I mentioned earlier. We could have found it by intersecting and graphing and etc. But you know what? This time I'm going to leave it with the logarithm explanation. See? It's about time that we faced things that maybe we don't like. I know that no one likes logarithms, but hey, at least I showed you one way in which it's actually really useful. So again, keep it in mind. If you have variables on an exponent, consider logarithms in order to get them out of the exponent, see? And so this whole process was just to get this guy eventually multiplying in front. So remember that this step here, we had this times the logarithm of just e, which we found out was just 1, see? So a little bit of logarithms, a little bit of things to learn here or there. The point is, logarithms are not that terrible, see? So learn logarithms, learn fractions, learn the unit circle. See, do all the annoying stuff. It's going to get you points, I assure you. Enough blah blah. That is for part D. And last but not least, we enter the last section of this problem. We have that as the T cools, h of t approaches the temperature of the room, which is constant. Okay, so if it means that it's constant, it's just one number like the entire time. See? And so we need to find the temperature of the room. And so this is, it's not exactly a context problem, but I mean, uh, you need to like interpret it correctly. See? And so one useful thing here is that this is a very repetitive question. See? There's a lot of different questions that are like after like a million years, like what does the population of like whatever rabbits like reach. See, or after the tea cools, like what is the temperature, or just very like long term stuff. See, and so the temperature of the room, well, you can make sure that you have the temperature of the room if you plug in a really big value for t, right? And so you first need to establish, because it's the IB and for the method points and etc., you first need to establish to get that method point, because it is worth 2 points, that you will be thinking of a very big t. And so t is going to go basically to infinity, see? But in practical terms, you're going to plug in a t equals, I don't know, like 10,000. See? And so I'm pretty sure that after 10,000 minutes, the tea will have reached the temperature of the room. Okay, that is the point that I'm trying to make here. You first need to establish that you know what you're doing for finding the temperature of the room. You're going to reach that after a really long amount of time. So just plug in a t that goes to infinity. And I mean, we can plug in infinity if we work with limits, but I'm not going to get into limits because I don't think it's worth it. But it will say, like, you need to leave clear that you know that you're just plugging in a very big number. See? And so here you can also put, like, very big number, just so that whoever is grading you knows that you know what you're doing. See? They need to, that's the thing about method points. Whoever's grading you needs to understand what you were thinking. And so for finding the temperature of the room, you reach it eventually after a really long amount of time. So first you can establish, dude, a t that goes to infinity, or you can also establish like, dude, just a very big t, a very big number. Given this context, it's definitely big enough. 10,000 minutes is definitely enough time. See? And so you can go ahead and plug in an h of 10,000 into your formula or equation, and you end up with 21 plus 75, sorry, plus 75 e to the power of negative 0.08, ah, negative 0.08 times 10,000. All right, so this will be the temperature of the room because it's just after a really long amount of time. See? So if you go ahead and plug this into your calculator, you end up with 21. Let me clear that for a second. So 21 plus 75e to the power of negative 0.08 times 10,000. And so this is pretty much going to be your room temperature. It's just going to be 21. See? So the room temperature, or the temperature after 10,000 minutes, is going to be 21. It's a very big number, so it's strong enough evidence. The temperature of the room is just going to be 21 Celsius. Okay? And if you look at the mark scheme, just so that we're all always in agreement, on the one hand, it's recognition that t goes to infinity. Now here, I know you might be stressing, thinking, dude, I didn't put that it was a t going to infinity, but I did put that it was a very big number. It'll work, okay? It'll work. You just gotta somewhere express that you understand that it's a very big number. You understand that it goes on sort of like forever. See? For example, even for part F, which is a little bit different, here it says like, on the one hand, you can just attempt to use large values of t. It's the same for t going to infinity. See? So t going to infinity is just large values of t. All right? So you got to understand that, okay, temperature of the room is just putting in a very big T. Or for some other exercise, as I was saying earlier, like population of rabbits in some forest, see, and they tell you like what is like the stable population, right? Like what does it converge to? Well, just put in a very big T value, because you're basically saying like, okay, after 1,000 years, like what's the population of rabbits? Like that's what you're doing, see? After 10,000 minutes, what is the temperature of my cup of tea? Dude, that's probably, I mean, that is the room temperature. After 10,000 minutes, you will reach the room temperature. In fact, I'd be even willing to bet you can plug in a little bit less, like 1,000, and it's still going to work. See, even with 1,000, you still get 21, see? And so, again, this is just a method point thing. And you can double check by plugging in other big numbers. So you do have your calculator, so you can also feel like good about plugging in a big enough number. But yeah, so the main idea I'm trying to give you here is that temperature of the room, you're taking like long term, just plug in a very big value for T. See? And here's another test taking strategy I'm going to mention. There's a lot of different tips and tricks that I try to give you guys. On the one hand, remember that in part AI, they were asking for the initial temperature of the T. So it was at T equals 0. And it's not that crazy that in the same problem, instead of asking a t equals 0, they're asking for a t to infinity. All right, and so it's a lot about interpreting functions, how it is at the beginning, how it is at the end, what does it converge to, what does it not converge to, and usually plugging in very big values for t or very small values for t helps you interpret that. See, and so be on the lookout. See, it's fairly common that they ask for an x for plugging in x of 0 or plugging in an x that is very huge. Just in this case, x is t, right? All right, that was a lot of blah blah, but I'm sure it helped someone out there, so that one's for you. See? All right, and now for part F, we need to find the limit of the derivative as t approaches infinity, right? And so this one is a little bit more hardcore. Here they do establish like putting in the limit, right? And technically you can do it with a limit, but as I said, you don't have to get so into like how limits work and the function of a limit and blah 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 and etc. Really, you just need to establish again for part F that you will be thinking of t going to infinity. So you're just going to plug in a very big value of t. I'm again going to plug in t equals 10,000 because I'm telling you that works. And again, it's just going to be a very big number. And so if you go ahead and take your derivative, right, and plug in 10,000 into it, well, we did establish earlier that the derivative was this guy here. And so you go ahead and plug in 10,000 there, you end up with negative 6 times e to the power of negative 0.08 times 10,000. And so this, actually, just by interpreting it, just very, uh, give me a second. It's hard to tell what this is going to be, but let's see. So if you go ahead and plug in 10,000 there, you end up with negative 6 times e to the power of negative 0.08 times that 10,000 that I mentioned. So eventually, it reaches something similar to 0. See, so it reaches something similar to 0. So h of 10,000 is just going to be 0. See? So you can basically say, and write in hand from here that like limit of the derivative of t as t goes to infinity, right, is 0. Okay? So basically, what this is saying, just to further expand on this, I did mention earlier, right? I did mention earlier that when you have the derivative function, you're now like discovering or finding slopes. And we also mentioned earlier that in the original function, you would always get 21. Whether you plugged in 10,000 or you plugged in 1,000, you would get 21. The room temperature is 21. And so it makes sense that even the slope ends up being 0 with a t that is very big because, surprise, your slope isn't changing. Surprise, you reached room temperature and you're not going to change from there. So that is why also plugging in a very big value for t in this context gives you a slope equal to 0 because you already reached the room temperature. You're not going to move from there. See? So guys, for these exercises of limits, I know it can be very scary to like do the limit function and solve it with limit properties and limits and blah 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 and dealing with infinity. But really, once you realize you're dealing with infinity, just plug in a very big number and forget about it. Like, I'm not even kidding. Like, that works, it'll do, it works. And that is also why I'm showing you the mark scheme in the face. You need to understand that for the IB, they take the large value of t as basically plugging in t to the infinity. Okay? So I really need to establish that. Just get it out of the table right away. If you plug in a very big value of t, the IB takes it as like t going to infinity. See? And just to make sure that you get the method point, once you realize you're doing that, write down somewhere t going to infinity. And even though you actually plug in 10,000 instead of infinity, they're going to get it like, okay, he understands the concept. See, which is why I had such a long monologue just now. You really need to understand the concept. If you're going for infinity, it's the same as just plugging in a very big value of t because the conclusion will be pretty much the same. See? There's some cases where not, but for the AASL level, I don't think you gotta worry about the weird cases. See, so just plug in a big value of t, it'll make sense. Don't worry about it. See, ladies and gentlemen, that was definitely a little bit of a longer explanation of number 7, but there's a lot of context to go over, and at least from the feedback I've received, you guys appreciate a longer explanation, so there it is. I hope it helped. I'll see you around. Take it easy. Bye bye.